Okay, so let's go ahead and take a look at relative extrema. And what relative extrema are, if you're given a certain function, let's say this is x and y, and you're given a certain function, let's say the function looks like this. Well, the relative extrema are the points that are at the top of the hills or at the bottom of the valleys. So they're not the largest values of all. This isn't the largest y value of all. This one here. As a matter of fact, there is no largest y value of all. These y values just keep getting larger and larger and larger. So it's not the absolute maximum. It's only a relative maximum. It's the tallest, it's the highest y value amongst all the values around it. So it's kind of like that old saying that in the land of the blind, the one-eyed man is king. So this is not the highest y value of all, but it is the highest y value of all around it. So it's called a local maximum, a local or relative maximum, okay? Not an absolute maximum, but a relative maximum. This one down here is also the lowest y value of all the ones around it. It's not the lowest of all because, of course, this function has no minimum, but it is the lowest of all the values around it. It is a relative or local minimum. So here we have a relative maximum. That's one kind of relative extrema. Here we have a relative minimum. That's the other kind of relative extrema. It doesn't have to be the smallest value of all. It just has to be smallest of all the ones surrounding it. So how do we find those kind of values? Well, here's a clue. If f of c, if that specific y value is a relative extrema of the function f, then x equals c is a critical value of f. So it seems as though relative extrema only occur at critical values. So one way of narrowing down where the relative extrema are is to find all the critical values for the function, because relative extrema only occur at critical values. So how do you find critical values? Well, first you have to know what they are. So here's the definition. So given a function f, like we have a function here, a polynomial, given a function f, the value x equals c is a critical value of f if these two conditions are met. So if first, f of c has to be defined. Well, we're in luck because polynomials have domain negative infinity to infinity, so this function is defined everywhere. So we don't have to worry about one because it's a polynomial. But part two says that f prime of c, the derivative, when you plug c in, has to give you 0, or f prime of c, the derivative, when you plug c in, has to be undefined. So we need to find all the places where the derivative of this function is either equal to 0 or where it is undefined. So let's go ahead and do that. So I find the derivative f prime of x is equal to 4x to the third minus 12x squared minus 40x and then plus 96. I get that from just applying the simple power rule to each individual term. So I need to know where this thing is either, this derivative f prime is either equal to 0, I need to know what x value that is, or where it's undefined. Well, once again, this is a polynomial, and a polynomial is never undefined. So all we really have to worry about is where f prime of c is equal to 0. In other functions, if the derivative were rational or some other kind of function like a radical function or one of the trig functions that have discontinuities, then we'd actually have to look at where the derivative was undefined also. But because it's a polynomial, we only have to look at where it's equal to 0. So here's what I'm looking for. I'm looking for where the derivative is equal to 0. X cubed minus 12x squared minus 40x plus 96. So here's what I have to do. I have to figure out what values of x make this true. So that's going to be a case of factoring. We're going to have to factor to get the zeros here because it's quadratic. I mean, not quadratic, cubic, because it's cubic, okay? We can't use the quadratic formula because it's not quadratic, it's cubic. So we have to factor. So one thing I see is that they all have a common factor of 4. So I can take out the 4 and be left with x cubed minus 3x squared minus 10x. And then that's going to be plus, what's that? 4 goes into twice 24. So we get this. So since 4 is a constant, 4 will never be equal to 0. But that means that I'm looking for what makes x cubed minus 3x squared minus 10x plus 24 equals 0. This is what I'm really looking for. That's the only factor that can contribute to this being 0. So how do we factor this? How do we find factors? Well, we have to go back to our college algebra and pre-calculus days. And in order to find zeros of this, what we're going to have to do is we're going to have to find all the possible rational zeros. So this would be p, and this would be q. Q would be 1, the coefficient of the leading term, and p is the constant. So what I need is I need to look at all the factors of p over the factors of q. So that's plus or minus. Well, one factor of p is 1. Plus or minus 2. 2 is also a factor of p. Plus or minus 3. 3 also goes into 24. Plus or minus 4 also goes into 24. Plus or minus 6 goes into 24. Plus or minus 7 doesn't go in. 8 does. 8 goes into 24. Plus or minus 9 doesn't, but 12 does. And the last number that goes into 24 is 24, plus or minus 24. So here's a list of possible rational zeros. The factors of p are all of these, and the factors of q are all just 1. So it's all these numbers divided by 1. This is a list of my possible rational zeros. I just have to figure out which one of the numbers on the list actually make this equal to 0. Well, let's go ahead and try the number 1. Well, the way that we do that is we use synthetic division. I put 1 in the little bracket, and then I put all the coefficients. 1, negative 3, negative 10, 24. So that's 1, negative 3, negative 10, 24. I try all the coefficients, and then I use synthetic division. So I bring this down. 1. 1 times 1 is 1. Here I get negative 2. 1 times negative 2 is negative 2. Here I get negative 12. 1 times negative 12 is negative 12. And here I get 12. So because this number is not a 0, 1 is not one of the values that makes my derivative equal to 0. So 1 doesn't work. So we try the next one. We could try positive and negative 1, but I'm going to go ahead and try positive 2. So let's try 2. Let's see, the coefficients were 1, negative 3, negative 10, and 24. So I bring down the 1. This is 2 times 1 is 2. This is negative 1 plus 2 is, or negative 3 plus 2 is negative 1. 2 times negative 1 is negative 2. Negative 10 and negative 2 gives me negative 12, and 2 times negative 12 is negative 24. So I get a remainder of 0, which means that 2 is one of the numbers that makes this polynomial equal to 0. So here was my derivative. This was what I got for the derivative. And I just found out that one of the numbers that makes this 0 is 2. If I plug 2 in, I'll get 0. You can check that if you want, but I'm pretty sure you will get 0 when you do this. This should equal 0, okay? All right, now we have to find the other 2 zeros because it's a cubic polynomial, so it should have 3 zeros. So the other zeros, let's see. Now that I've found out that positive 2 is a 0, that means one of my factors is x minus 2. X minus 2 is one factor. And the other factor is going to be, well, these are going to be the coefficients of my other factor. And if I take out a linear factor out of a cubic polynomial, the other factor has to be quadratic. So it's going to be 1x squared, 1x squared, minus 1x, minus 1x, and then minus 12, minus 12. Well, thank goodness this one is quadratic now, so I can continue to find my other factors. Let me see, I already have the factor of x minus 2. X minus 2 corresponds to the 0 I found from synthetic division. Now I'm going to factor this part, x squared minus x minus 12. Well, let's see. The two factors there, to get x squared, I need an x and an x. And to get a negative 12, I can use a negative 4 and a positive 3. And if you go ahead and FOIL this, you'll realize it is x squared minus x minus 12. And if you multiply that by x minus 2, you'll see that you get this x squared, x cubed minus 3x squared minus 10x plus 24. And then if you go through and you multiply that by 4, you will get the original polynomial. So the factor that I have missing here that I didn't write in, remember there was a factor of 4 that I took out of everything. So that factor of 4 is what makes this equal to the original derivative. So if you multiply all these things out, 4 times x minus 2 times x minus 4 times x plus 3, you will indeed get this derivative. You will indeed get this. So that gives me my other two zeros. I know that x equals 2 was a 0. That's one of the things that makes my um, polynomial equal to my derivative equal to 0. I also know that positive 4 is a 0, because if I plug 4 in here, I get 4 minus 4. That would make this entire thing 0 also. And I also get negative 3 as a 0, negative 3. So these are the three numbers that make the derivative equal to 0. If you plug any of these three in, you get 0 in this polynomial, okay? So these are my critical values. The critical values, remember, given a function x equals c is a critical value of f if, well, first it has to be defined. All those numbers are defined. You can plug all those numbers into the original. And also, f prime of all those numbers, if you plug all those numbers into the derivative, you will get 0 as the answer. That's how we did it. We used synthetic division to find the zeros. Okay, so once we find the zeros, here's what we're going to do. To find relative extrema of the function, we're going to have to know where the function is increasing or decreasing. The numbers we just found, the critical numbers, actually set up intervals, open intervals, on our x-axis. Here's what I mean. So here's my x-axis. I have the number negative 3, I have the number positive 2, and I have the number positive 4. I have there 3, or actually 4 different intervals. I have the interval from negative infinity to negative 3. That's one interval to the left of negative 3. I have the interval between negative 3 and positive 2. That's the interval between negative 3 and positive 2. The interval between 2 and 4. Interval between 2 and 4. And also the interval between 4 and positive infinity. So what I'm looking at here, I have 1, 2, 3, 4 open intervals created by my critical numbers. What I want to know is I want to know if the function is increasing or decreasing on these intervals, okay? Because whatever it's doing for that entire interval. So I need to use the derivative. Remember, here was my derivative, right? I need to use the derivative to find out if the function is increasing or decreasing on those intervals. So here is my derivative once again. This is my f prime of x in its factored form. What I'm going to do is I'm going to choose numbers on each one of these intervals, plug them into the derivative, and if the derivative is positive, if the derivative gives me a positive number, then the function is increasing. So if f prime of x is greater than 0 at that particular value, then I will say the function is increasing on that entire interval. And also if f prime of x is less than 0, negative for that interval, then I'll say the function is decreasing on that interval. So let's look at each individual interval. I'm going to choose a number on this interval. A number between negative infinity and negative 3 is negative 4. So I'm going to find the f prime of negative 4. That's 4 times negative 4 minus 2 times negative 4 minus 4 times negative 4 plus 3. Now, I don't really need to know what the actual number is. I just need to know the sign. Okay? So I'm going to look at the signs of these factors. This is positive. 4 is positive. This factor here is negative. This factor here is also negative. And this factor here will also be negative. Positive times 3 negatives gives me a negative answer. So I don't really care what the number is. All I care about is the fact that it's negative. So on this interval here, the derivative is negative, and when the derivative is negative, the function is decreasing. So on this interval, I know the function is decreasing. Decreasing. All right, now I'm going to choose a number on this interval, the interval between negative 3 and 2. A number on that interval is 0. So I'll find the f prime of 0. The f prime of 0 is going to be 4 times 0 minus 2 times 0 minus 4 times 0 plus 3. And let's see. That's going to give me positive for 4. 4 is positive always. 0 minus 2 is negative. 0 minus 4 is also negative. And 0 plus 3 is positive. So I have a positive times a negative times a negative times a positive, which gives me a positive answer. So on that second interval, the function is increasing. Increasing. All right, so let's see. Let's look at a number on this interval from 2 to 4. A number on the interval from 2 to 4 is 3. So let's find the f prime of 3. That's going to be 0. Well, not 0. It's going to be 3 minus 2, 3 minus 4, and 3 plus 3. Let's see what we get here. This is 4, positive, right? It's positive 4. And then this is going to be positive also. This one is going to be negative, and this one is going to be positive. So I have a positive times a positive times a negative times a positive, which gives me a negative answer. So on this interval, the function is decreasing also. And on the last interval, a number between 4 and infinity is a number like 5. So I need the f prime of 5. It's going to be 4 times 5 minus 2 times 5 minus 4 times 5 plus 3. So on this interval, I have positive, 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 and positive. So the answer is positive. So now I know on this interval here, this last interval, the function is increasing also. So there I have all this information about increasing, decreasing, and increasing on different intervals. Well, here's what I'm going to do with that information. It turns out that the first derivative test says that given a function f that is continuous on an open interval I, containing critical value x equals c. I found all the critical values. If f is differentiable for every value on the interval except possibly at c, then if f changes from decreasing to increasing at c, then f of c is a relative minimum. But if f changes from increasing to decreasing, then f of c is a relative maximum. That's the first derivative test. So based on that, I have this information here. So you can see that the function f goes from decreasing to increasing at -3. You see that? -3 on the left of -3 is decreasing, on the right of -3 is increasing. So if it goes from decreasing to increasing, then it's a relative minimum. So f has relative minimum. So f has a relative minimum at x equal -3. Also, if you take a look, it's decreasing to increasing at 4 also. So it's also and at x equal 4. The other thing says that if it goes from increasing to decreasing, then you have a relative maximum. So here at 2, you see at 2, on the left of 2 is increasing, on the right of 2 is decreasing. So there's a relative maximum at x equals 2. And if you notice over here also, let's see, goes from increasing to decreasing. Oh, there's no other place where it goes from increasing to decreasing. So basically, this function has 2 relative minimums and 1 relative maximum at these values. If you wanted to know what the relative mins and maxes were, you just take these x values and plug them into the original function. And that is the first derivative test.